Welcome to CS420, Lecture 10. At the beginning of the lecture notes, there's this couple of paragraphs that talk about abstract data types. One thing that we might call this today is an API. An API is the interface and how we use something, and we usually don't care about how it's implemented as long as it works for us. So that's what we're going to be talking about today, is a new abstraction to create our own types. Now if you read down through here, you'll see an example of a problem when we don't have types. If we have an S list defined by this BNF, and we have a binary tree defined by this BNF, when we look at this, we don't know if it's a binary tree or an S list. And what happens if we have an S list that contains binary trees? And so it wouldn't be quite a S list, but maybe we have a number, symbol, or some other element. Maybe we can add binary trees in here. But then we wouldn't know, there wouldn't be a way to separate our productions because we wouldn't know if what we're looking at is an S list or a binary tree, because the only test we have is to test to see if something is a pair or not. So read through this and make sure you understand it before we move on. So we can create a new type with the define data type function. Now the define data type function will only work if you're using EOPL. If you're using Racket or something else, it won't work. So make sure you have lang EOPL at the top of your file to get the define data type. So define data type is used when we want to create our own type. Now you've done this in other languages, especially object-oriented programming languages, where you create a class. So a class defines a brand new type that you can use in your language. And then if you want a type of your class, then you have to instantiate it or call this constructor. In this case, we are defining a new type, which is kind of like defining a new class. The class name or the type name is bin tree, short for binary tree. Right here will create us a new predicate where we can ask if something is a binary tree. And if you don't know yet, Racket has all of these built-in types or predicates to determine if something is a certain type. So symbol question mark, number question mark, pair question mark, list question mark. And so when we create a new type, we'll also get a new function or predicate to say that will tell us if something is that type or not. Now this way of defining types, or this interface that we have to define types, is really good for defining inductive types. Inductive types are types that we define with a BNF. So if you look in your lecture notes, we have this BNF for a binary tree. And if you notice, there are two variants for a binary tree. We have a leaf node or a interior node. So the way of defining types, or the define data type, works really well for this. Now sometimes we want to define a type that only has one variant, but we're still stuck with define data type. It's the only way that we'll use in this class to define a new type. So in that case, you have to come up with two names. One name for the type, like bin tree, and one name for a variant. Even though there's only one of them, we need a name for it. Now, but in this case, a binary tree, we actually have two different variants. We have the leaf node and an interior node. So we need to come up with a name for each variant, which I just did, a leaf node and an interior node. And then what comes next is the data that we want to store inside of that variant. Notice a leaf node, we just want to store a number. And this right here is any name we want to give it. So the data inside the leaf node, I'll just call it a datum, and it has to be a number. And so there has to be two things here. Notice it's surrounded by parentheses. There has to be two things. The first thing is a name, and the second thing is a predicate. And in order to create a leaf node, it will type check the datum to make sure it really is a number. Because we don't want to create a binary tree that doesn't follow the right format. So this forces us to store only numbers inside of a leaf node. If we look at the interior node variant, it stores three different things. It stores a key, which has to be a symbol type. It stores the left tree, that has to be a binary tree, and the right that has to be a binary tree as well. And notice, yes, we can use the variant or the predicate that we create when we define the data type inside of the same data type. Now I'm going to summarize this one more time just to make sure you know what each piece means. So we're going to define a new data type. What's the name? A bin tree or a binary tree. So this is like in Java, you're saying a class and you're giving the class a name. The next thing that follows is the name that you want to give the predicate that will test, and it will return you true or false. If you have anything in Racket, you can call bin tree, pass that thing in, and it will tell you true if it is a binary tree or false if it is not. So you can decide the name, but you should probably use the same name as your class or your new type and put a question mark at the end, like all predicates in Racket. Next, we have the name of our variant. And inside, so notice it open parenthesis and a close parenthesis, and inside is a list or all of the data that we want to store with that. So a leaf node, we just want to store one piece of data. So you give it a name and a type. By the way, this name we'll never use again, but it's good to have it there just for documentation so you know what things are. Like in the interior node, you know, okay, that's the key, then the left and the right. It makes it more readable. So in the interior node, notice if we store more than one data, we just add another set of parentheses and add the next data there. Of course, with the name and the predicate or what type that thing needs to be. So when we run this, nothing happens other than we have a new data type. When we do run it, it gives us three new functions. The first function is a binary tree question mark. So you could go ahead and type that down here and you could see that it is a function. And we can ask it, is 5 a binary tree? And it's like, no, 5 is not a binary tree. So it works with any, we could pass anything, any data from Racket in here, and this should return true or false. Now the other two functions that are created, and in this case it's two because we have two variants, are constructor functions. These are ways to instantiate or create something of this new type. So we have a leaf node function and an interior node function. And if we want to build a new binary tree, all we have to do is call our constructor. In this case, I'm creating a leaf node binary tree and then pass it its data. And you can see that we now have a leaf node. And if you know C, a struct is kind of what predated a class, but a struct is a way of creating a new type. And inside Racket there are structs, but we won't use them in this class. Other than the structs that we get from instantiating something of our own type with this defined data type. So this is the only place that you'll use a struct, but it's all going to be hidden away behind the defined data type. So another thing to know is just to show you that this bin tree really does work. If we pass in a leaf node, which is one of the variants of a binary tree, it will tell us true. Yes, this is a binary tree. We can also pass in an interior node. So in this case, I'm defining an interior node, but notice an interior node requires two other binary trees. So I'm going to create two leaf nodes, one to be the left binary tree and one to be the right binary tree. And now I've created an interior node with two leaf nodes. When you click run, and I can type my tree, and I typed it up here so I don't lose it. I can keep referring to it as my tree instead of typing this in over and over again. You can see that we have all of that data inside. Another thing that we can ask is an interior node, or my tree, a binary tree, and yes it is. And we can also expand this. Maybe we can make this left tree right here. We can make it an interior node instead of a leaf node. So now my tree is a node A that has a left tree and a right tree. The right tree is just a leaf node with 2 inside, and the left tree is an interior node called B, and it has a left tree with 5 and a right tree with 7. And we can click run, and when we type my tree, we can see all of that information inside. And of course we can ask if it's a binary tree, and sure enough it is. Now I did want to show you, what if I don't give a right type? Notice the key needs to be a symbol. What if I try to make it a number instead? And you can see that it's a bad value for the key field. And so that's the type checking. It calls this predicate function and that returns false. And it knows that it cannot make an interior node unless it has a symbol, a binary tree, and a binary tree. So you can see that type checking taking place. Okay, now that I have a binary tree, how do I get the data out? How do I get its name or the numbers in the leaf nodes? How do I get that information out? And there's only one way to do it, and that's with a cases statement. Now this is actually going to work really well for our recursive programming. So remember the 5 steps to writing a recursive program? Separating out the productions, step 2, is automatically done with our cases statement. We automatically know whether we have a leaf node or an interior node. The only unfortunate thing is, if we're not really writing a recursive function, but we do have one of these data types, we still have to do a cases and we still have to do this. Now if we only have one type, let's say our binary tree only had a leaf node to it, then our cases would only have one type too. So it's a little weird seeing a switch statement when there's only one option. But that's all we have to work with. But these things are really great when we're doing our recursive programming, which we're going to be doing a lot of. They're a little bit awkward when we only have one variant, and we're not doing recursive programming because we're doing a switch statement when we already know exactly what it is. But that is all we have to work with, and we can handle that. So how does this cases work? Well, first we have the word cases. Second is the name of the data type that we're going to try to take the data out. So in this case we have a binary tree, so we just put that there. So this is our class name. If you are referring to creating a data type like creating a class, that's the name we're giving it, so that's what goes next. The next thing that comes here is the name or the data itself. So when we call leaf sum, we're going to pass in one of these types, and that's the name we give it is tree, and that becomes the third thing we put there. So cases, the name of the type, and the actual data. Then we have one parenthesis to parenthesis for each variant of that type. Now there is a default, so if we have like 10 variants and we only want to deal with 2 of them, we can have a default as well. But in this case, there's a leaf node type and an interior node type. So we could go ahead and run this, and we could try to call leaf sum on a leaf node with 7 inside. So this leaf node creates a new binary tree with 7 stored inside. The cases asks what type you are. It says I'm a leaf node, and inside of this parentheses are the names that we want to give the data inside of that leaf node. So remember, step 3 is to break apart compound data when writing recursive programs. Well, that's done automatically for you too, because we just give each data stored inside of it a name. Now notice this name does not have to match up with that name, but it can if we want. And again, I don't recommend using just one letter for names, but I just want to show you that this name, you can name it whatever you want. So you can name it D, we can name it datum, we can name it num, but it is in the order we define it. So on the interior node, the first one is always going to be the key, the second one is always going to be the left tree, and the third one is always going to be the right tree. So we can give it 3 names. So let's go ahead and try leaf sum on my tree. And we see that we get A because that's the key of the interior node, and that's what I'm returning. So this thing right here is whatever we want to return. In this case, I'm just returning the data out. But we can expand this. We can make this another expression. So we can add 5 to our number. And make sure we close the parentheses. And we can run this. And when we're passing in a leaf node with 7, it will take the 7 and add 5 to it, and we'll get 12. So this can be a very long, complex expression, or it could be as simple as just returning the number. Now let's finish out this function. What we want is a function that adds up all of the numbers in our leaf nodes and returns us the total sum of the leaf nodes. So we're following the 5 steps for writing recursive programs. Step 1 is to name the function or create a function. Step 2, already done by our cases, is to separate out which production we have. Step 3 is to break apart compound data, which is automatically done for us by this syntax right here. We got the key, the left tree, and the right tree. In the case of a leaf node, we get its number out. And then, so we've broken apart compound data. Next, we want to recurse, so that's step 4. So this is a binary tree, and this is a binary tree. So we're going to recurse on the left and the right trees. Now remember, k, even if I want to call k left, it's not going to be the left binary tree because it's in the first position. Left would be our key. So it has to go in the same order that you defined it. So our key, our left tree, our right tree, we're recursing. Step 5 is to combine the results. So we're going to get the sum of the left tree, the sum of the right tree, add them together, and return that as our answer. So all of this that I highlighted is what we'll do if we have an interior node. So let's go ahead and run this and see if it works. Of course, we're running the leaf sum on my tree. And we can see that 5 plus 7 is 12, plus 2 is 14. And we can also run it on just an interior or a leaf node, and of course we get the sum of 7. So in this case, we do a cases on what kind of tree it is. It's a leaf node, it just returns 7. If it's an interior node, it recurses on the left and the right trees, gets their sum, adds them together, and returns that. Now the EOPL package that gives us this defined data type also gives us another function called listOf. You can see the code of that function in your lecture notes right here. This is a great example of querying that we introduced in lecture 4. So if you remember lecture 4, we talked about querying. You might have wondered why we do this and why it's so powerful. The cool thing is listOf can create us new functions. List of symbols is now a new function, and we can call that function and it will return true or false whether or not this is a list of symbols. In that case it was just a symbol, but in this case it really is a list of symbols, and if we put a number in there it'll check it and it'll say nope, that is not a list of symbols. The cool thing is we can create another function to see if something is a list of numbers. And in fact, we can even create another thing. Let's say we had a list of binary trees. We can create a function that checks to see if we have a list of binary trees.